Welcome to today's Explainer. I am super excited to be your tutor today because we're going to demystify some truly fascinating physics. We're tackling the root mean square velocity of gases. I know, it sounds like a handful, right? But don't worry. Together, we're going to take a guided, step-by-step walkthrough to completely break down the abstract math behind how fast gas particles are actually moving. So, let's dive right in.
Okay, so here's our roadmap for today. We'll start with the zero-velocity paradox, uncover the clever RMS solution, and then clash two major physics theories together. After that, we'll walk step-by-step through the derivation, unlock the three master formulas, and finally, connect the whole shebang to temperature and molar mass.
All right, Section 1, the zero-velocity paradox. Let's talk about why average speed is mathematically zero. Okay, imagine this. If gas particles in a sealed container are randomly zooming around at literally hundreds of meters per second, why on earth is their average velocity exactly zero? I mean, it sounds totally absurd, doesn't it? We've got a container full of these rapidly moving particles, but if we just average them out normally, mathematically we get absolutely nothing. Let's take a look at why this weird mathematical quirk happens.
Well, you got to remember that velocity is a vector, and that just means it has a direction. So, inside our container, for every single particle moving to the right with a positive velocity, let's call it plus v1, there is almost certainly another particle moving to the left with a negative velocity, minus v1. When we calculate a standard mathematical average, we just add everything up. But what happens when you add positive v1 and negative v1? Boom, they perfectly cancel each other out to zero. So yeah, standard averaging completely fails us here.
Which brings us to Section 2, the RMS solution. This is where we reverse the math to find the truth.
Here is the secret workaround physicists use. Even though the term is root mean square, I highly advise you to read the math backwards as SMR. First up, we square all the individual velocities. Squaring a negative number makes it positive, right? Which beautifully eliminates that whole cancellation problem entirely. Second, we take the mean, or average, of all those newly positive squared numbers. And finally, step 3, we apply a square root to that average, and that returns our answer right back to its original useful velocity units. It's a really clever trick. Now, before we jump into the full derivation, I want you to focus on this exact definition: mean square velocity. Notice how pausing just before we apply that final square root in step 3 gives us this specific value. It's simply the mathematical average of the squared velocities of all the molecules. We actually usually denote this with a little bar right over the v squared. Definitely keep this concept fresh in your mind because it's a super crucial stepping stone we're going to need in just a moment.
Moving on to Section 3, clashing two physics theories. It is time to set up the ultimate equation.
I want you to imagine a balancing scale. Over on the left, we have a formula derived from the kinetic theory of gases. Pressure times volume equals 1/3 times capital N times m times our mean square velocity. Then on the right, we have the legendary ideal gas equation. Pressure times volume equals capital N kT. Notice what's really interesting here. Both of these totally independent theories equal the exact same thing, P times V. And this equivalence is the anchor we need before the algebraic shuffling begins.
Now, please don't panic when you see these new variables popping up. I've put together this really simple substitution legend for you. K is just the Boltzmann constant, which is the universal gas constant R divided by Avogadro's number. Little n is the number of moles, and capital M is the molar mass, which is simply the mass of one single molecule, little m, multiplied by Avogadro's number. Keep these relationships in mind, as we're going to use these exact substitutions to adopt our algebra later on. You're doing great.
All right, here we go. Section 4, step-by-step derivation. Let's solve this puzzle together.
So, since both of those original equations equal pressure times volume, we can set them perfectly equal to one another. We get 1/3 capital N little m v squared perfectly equals capital N k t. The left side is our kinetic theory, and the right side is our ideal gas behavior. It's literally two physics worlds colliding.
And now for honestly the most satisfying part of the math. Notice that we have capital N, which represents the total number of molecules on both sides of the equation. That means we can beautifully cross it out, completely canceling it on both sides. With the N gone, we can isolate our mean square velocity by moving the 3 and the m across the equal sign. Just picture moving that little m to the denominator on the right side. That leaves us cleanly with v squared equals 3kt all divided by m. We are so close to the finish line.
But remember, the equation we just isolated was only the mean square velocity. We still need to finish our SMR method. To do that, we just apply the final root to both sides. By taking the square root, you can visualize the square on the v just dropping away. And boom, we arrive at our first big formula. Our root mean square velocity, VRMS, is exactly equal to the square root of 3kt over m. Absolutely fantastic job following along with those steps.
Next up is Section 5, the 3 master formulas. Let's see how this adapts to different variables.
So depending on what starting variables a problem gives you, our base equation actually morphs. If a problem gives you temperature and the mass of a single molecule, use our base formula, the square root of 3kt over little m. But if you substitute in the universal gas constant and molar mass, the equation brilliantly adapts into the square root of 3RT over capital M. And finally, if you swap out mass and volume for density, it adapts yet again into the square root of 3 times pressure over density, or rho. It is the exact same fundamental mathematical truth, just wearing 3 different outfits to help you solve different physical scenarios.
And our final part, Section 6, temperature and molar mass. Let's talk about the real-world physical meaning of all this math.
Because temperature, T, is sitting right there in the numerator under the radical, RMS speed is directly proportional to the square root of temperature. What that means quite literally is, heating a gas makes its particles move faster. Conversely, because molar mass, m, is in the denominator, RMS speed is inversely proportional to the square root of molar mass. This essentially tells us that a heavier gas molecule is always going to move slower than a lighter one, even if they're heated to the exact same temperature. Makes sense, right?
To really hammer this crucial point home, let's look at this direct quote from our sources. If you increase the temperature, you will increase the root mean square velocity of the gas. It's just a beautifully direct relationship between the thermal heat you apply and the pure, kinetic, zooming movement of the invisible particles inside that container.
To wrap up today's explainer, I want to leave you with a bit of a provocative thought experiment just to test your attention. If you take a gas in a sealed container and you perfectly double its temperature, what exactly happens to its final RMS speed? Well, remember, temperature sits underneath a square root sign in our master formula, so doubling the heat doesn't just neatly double the speed, it actually increases the speed by the square root of 2. Think about the incredible implications of that as things get hotter and hotter in our universe. You all did an amazing job walking through these derivations with me today. Keep asking those great questions, and I'll catch you in our next explainer.